Hello, good morning. Welcome to the, day 2 of your, generative AI from C3 AI. My name is Aaron Saxton. I'll be hosting or chairing the first few talks here. And so to get started this morning, I want to introduce Tatsu Hashimoto. He joins us from Stanford, the computer science department at Stanford. And this morning, he's going to tell us about improving instruction following language models. So with that, I'll let you take it over. Thank you.
Thank you very much. Okay, good. Everyone can hear me. So I want to talk today about black box, instruction following language models and how we might sort of build better scientific understanding of them. So to set the stage, in some sense, on day 2, this feels very redundant. But language models have really taken over in many ways. I think many of you have probably started seeing some of the changes that this system has made, starting with ChatGPT. But even starting with, I think, GPT-3, sort of the seeds of things being different were already there. And now, with the release of GPT-4, there's all these claims about how these systems are now, let's say, human level on a variety of professional exams and difficult tests. And this is really amazing. There's really useful products and interesting capabilities being advanced by these systems. At the same time, we see that these models are increasingly closed off and difficult to understand for basically everyone involved. On the top left, I'm showing a screenshot from an article about how the GPT-4 tech report doesn't contain many details, both for safety and competitive reasons. On the top right is a Twitter post. Unfortunately, I have a few Twitter screenshots in this talk of at least me finding out that one of the API models doesn't correspond to a baseline that was in the InstructGPT paper. And of course, I've highlighted OpenAI because they're, in some sense, the biggest player in this space. But they're far from the only ones having this problem. On the bottom here is sort of a little transparency scorecard for the EU AI Act that some colleagues at Stanford made. And what you see is that basically none of the proprietary vendors give very many details about the training of their model, their data mixture, any of these things, right? So we understand very little about the actual, really low-level details of these systems. And what exacerbates this problem is that the training processes and the deployment contexts of these systems are getting increasingly complex, right? Training an instruction tuning model involves multi-step human feedback system in which you're collecting supervised fine-tuning data and then applying a reinforcement learning algorithm on top. And these processes are pretty finicky. You have to tune these algorithms carefully. You have to think carefully about what data you're going to collect. And so that makes it hard to understand even basic questions like which part of this pipeline is important. We're also deploying these systems in much more complex environments. Because these language models actually work, people are shipping them to actual end users, and we're hooking them up to things like APIs and tools, right? These are much more complex environments than something like an academic benchmark, in which all you're doing is generating some text and measuring similarity to some reference, right? And so understanding both the training and the deployment situations of these models, I think, is becoming increasingly difficult. And this is compounded by sort of the lack of transparency from these vendors. And so at least my view of what's sort of important research in this space is that if we're going to be responsibly using and deploying and developing large language models, we require sort of a deeper, generalizable knowledge and some understanding. And to do this, we need better tools to replicate some of these training behaviors. We need tools to analyze what is going on within them. And then we need to be able to audit them for certain kinds of behaviors that we think may be problematic. And so I'm going to talk about 3 different works in this talk. In the first part, I want to talk about some efforts from my group and collaborators on replicating and improving instruction following language models, a project which we called Alpaca Farm. And the idea here is that we're going to try to do an end-to-end replication of the instruction tuning process where we're going to use language models as sort of emulators of, say, tools or human annotators, hopefully making the cost and sort of replicability of this process substantially better. In the second part, I want to talk about sort of probing language models for who they emulate. If we view language models as in some sense replicating or modeling distributions of text on the internet, those texts were originally written by different people. And then we're applying this kind of feedback process on top of it And sort of Misha showed a nice figure in the talk yesterday about this Shoggoth of like layering things on top. And so you might wonder, okay, so then who exactly are these language models emulating? So we build tools to try to answer that question. And then finally, these models are pretty amazing. They pass, professional exams and so on. But increasingly, there's been sort of questions and concerns and even some accusations that these models have been trained on the test sets that they're evaluated on, right? So how do we make sure that the evaluations that we're running are clean in the classical statistical sense? And so I'll talk about some very recent work on basically trying to do external audits or provable guarantees for this kind of test set contamination. So, okay. I'll get started with the very first work. The high-level idea of this part is basically to try to use language models to, in some sense, empower language model research, to use them as simulators for replicating instruction following models. And this is joint work with a number of my students and collaborators, including Percy, Carlos, and Jimmy. So, many of you already know this, so I probably don't need to go through these 2 slides in detail, but the language model training process proceeds in 2 very basic steps. In the very first step, in which we're building a base language model, what we do is we build, in some sense, the world's largest autocomplete system, right? So we have an autoregressive model that continually predicts the next word. And so this large-scale pre-training, in which we're predicting the next word, powers very much a lot of the recent advances in language modeling. At the same time, simply mimicking random people on the internet is a very poor basis for building, the next generation AI system or whatever you might want to use language models for. And so on top of this, all of the major vendors do some form of feedback or fine-tuning steps in which we explicitly reinforce desired behaviors identified by certain crowdsourced workers. This is a figure taken from the InstructGPT paper in which they identify sort of 3 steps. In the first step, one uses supervised fine-tuning. So they have labelers give expert demonstrations on what's desired behavior. In the second step, labelers basically give thumbs up, thumbs down ratings on different outputs from the model to try to figure out what is desired behavior. And then in the final third step, a reinforcement learning algorithm is used in order to try to train the model to encourage good behaviors and discourage bad ones, right? So in some sense, a fairly simple setup, but at the same time, there's multiple steps of humans in the loop, and everyone knows that reinforcement learning is a pretty tricky thing to get right. And so I think maybe December or November last year, I think there was a lot of debate among my students and people at Stanford, like what makes InstructGPT work, right? And because there's many pieces of this pipeline, like who knows, right? Is it the quality of the supervised fine-tuning data in the first stage? Is it the use of pairwise feedback in the second stage? Is it clever tuning of the reinforcement learning algorithm? Do we even need reinforcement learning, right? These are fairly basic questions, right? Like we should know the answer to these things, but we did not know the answer to any of these things. And as far as we could tell, there wasn't very much in the way of like a replication effort for InstructGPT at the time anyway. And so our goal to start with was to try to replicate the InstructGPT training process, and not only to go through and do this replication once, but to build generalizable tools that would allow us to continue to do this replication process for future systems, for future base models, right? We wanted to build essentially a framework to enable this kind of study. And doing this is complex, right? Because in some sense, we need to be able to collect these kinds of annotations. Reinforcement learning, step 2 over here, this is model dependent. And so we can't just collect the static data set. So that leads to several major challenges. First of all, we know that OpenAI spends a substantial effort in collecting data sets, right? And so how can we collect diverse large sets of instructions that in some sense gets anywhere close to the kinds of data sets that these people have? Second of all, how can we get reliable sets of pairwise feedback? As I said before, those thumbs up, thumbs down ratings, those are model dependent, so we can't just collect these statically. And then finally, reinforcement learning is a pretty tricky algorithm to get right in practice, right? Can we use an off-the-shelf algorithm, or do we need to do some re-implementation? These are, in some sense, details, but very important details if we want to understand some of these questions. And so the high-level conceptual approach that we took was to try to build a simulator for reinforcement learning for human feedback. And the analogy that I want to draw for you is in environments that are dynamic, where you have these sort of reinforcement learning steps being executed, there's been a long tradition of using sort of simulators to make research more replicable and to make research more straightforward, right? Think of things like Mujoko or Carla for autonomous driving research. So in this case, we have 3 different components here. In the first step, in which we're just doing supervised fine-tuning and imitation learning, we built a model called Alpaca, which in some sense is a baseline for the rest of the work. In the second step, for reinforcement learning, we basically have a way of simulating pairwise human feedback. And in the third step, we need to be able to evaluate different models very quickly to be able to do R&D. And so we have an automated evaluation metric based on language models. And if we put all of this together, the experiment cost for being able to do sort of an end-to-end RLHF run lowers down to, let's say, $70 in annotation cost versus like $3,000 to much more depending on which annotation group you use for humans. And the iteration time for this becomes hours instead of days. And so, I'll go through each of the challenges that yes? $70 is just the annotation cost. So we have an additional compute cost, which I think is on the order of like $100 to $200. I need to get the exact number, but it's definitely less than 4 digits.
Annotation done by humans.
And the annotations are, humans for the $3,000 row. That's right. Okay, so now I'll go through each of the challenges. In some sense, I think the supervised fine-tuning step was one of the trickiest to get right. Mainly because there's 2 components to doing imitation learning, right? We need the X, which is the input, and Y, which is the output. So getting the output actually is pretty straightforward. We can query instruct GPT itself and basically get reasonable instruction following outputs, right? So getting the outputs are straightforward. Getting the inputs or the instructions themselves are actually much more complex. And so our approach was to use a prior work by some group from UW called self-instruct, in which we basically have a LM brainstorm the tasks from a seed set. So we have the 175 self-instruct seed tasks. We then use instruct GPT or text DaVinci 003 in our case to generate 52,000 examples. And then we also get sort of the responses out from instruct GPT, and we supervise fine-tune Meta's llama model. So this gives us Alpaca 7B, which was a surprisingly good instruction tuning model in the March of last year. And of course, for us, this is basically a baseline to do the rest of our reinforcement learning research. But it was actually surprisingly good. When we first trained this model back in March, we were pretty surprised by the performance of the system, and we put it online, and that went much further than we originally expected. But more scientifically, I think, interestingly, this kind of approach of using language models to generate sort of training data has kind of taken on a life of its own. And I think we've been starting to see some really interesting work on using language models as ways to to test different hypotheses about data-centric questions. And this work by MSR researchers on basically generating textbook-like data sets to train language models is a really interesting step in that kind of a direction. So now, with sort of this Alpaca trick, we have supervised fine-tuning data, and that's very nice because that gives us the baseline from which to build up a lot of the RLHF research we want to do. The second challenge that we now have is that we want to build sort of a way to get pairwise preferences out from language models, right? Because we now need to emulate the second step of having humans give thumbs up, thumbs down ratings for our outputs from language models. So now the question is, can we use a really powerful language model like GPT-4 to build an essentially useful simulation environment for human feedback in annotation? And it turns out this is really just like a prompting exercise. But we did try to do this as carefully as we could. We basically built, we went through probably dozens of prompts on 3 different models, GPT-4, ChatGPT, and DaVinci 003. We carefully looked at different correlations versus humans, and we find essentially that the GPT-4 annotator can get, correlations on par with humans on an average level. We also basically know that there's a lot of confounding that can happen in these cases, right? Like maybe, GPT-4 has a high correlation just because it prefers lists or longer outputs or, what the ordering of the answers that you're asking to pick. And so we basically make sure that, the simulated outputs that we get from GPT-4 are calibrated with respect to humans, right? So when we look at this, we basically see that the preference for lists is basically the same as humans. So humans is the blue square. And the GPT-4 annotators are the other colored boxes in this plot on the top right. Preference for longer outputs is also very similar to humans. One thing that we found to be very interesting, initially when we ran these studies, we thought that we had something fundamentally broken because the GPT-4 annotator just really preferred longer outputs. But what we actually found was that humans also really prefer longer outputs. And so finally, the third challenge that we have is in basically trying to find good baselines. When we started trying to do this replication effort, the stuff that we found was mostly basically targeting really old work from OpenAI on doing summarization using reinforcement learning. And so what we ended up having to do is to build our PPO models from scratch, and we found some, several details that were quite different than sort of the publicly available PPO implementations that people have had about normalizing advantage and so on. I won't go into too much detail on some of those details, but we basically had to redo some of this stuff from scratch. And so now we put all that together. I've given you a lot of this technical details. Hopefully I haven't lost you. But the interesting meat, I think, of this work is validating that this actually works. So I'll give you different validations of the same thing. The one end-to-end validation, maybe the thing you should remember and look at if you're interested in sort of just one number here, is the left plot over here in this slide. So what I'm showing here is in some sense the true end-to-end validation. On the x-axis is we train all of the RLHF models using simulated feedback. We evaluate it using the simulator, right? Everything is automated. On the y-axis, everything is done with humans. We get human pairwise feedback and we have human evaluations, right? So there's no simulator involved. If our simulator is in some sense faithful to the underlying behavior of humans and the evaluations and so on, we should get a perfect line on the x equals y, right? And each point over there is a different system that we're training and evaluating. And we actually see that the correlation is quite high, right? So that the end-to-end sort of faithfulness of the system is actually pretty good, at least at a rank level. When we look at individual ratings of our pairwise feedback, we also find that humans, the blue square on the top right, has similar correlation to our GPT-4 annotators, which are the colored boxes that we see here, and it's much cheaper, right? That's the x-axis over here. It's about an order of magnitude cheaper. We also see very interesting complex behaviors replicated in this. So there's this really interesting thing called over-optimization that OpenAI likes to really talk about, in which if you train a model using reinforcement learning, on the x-axis, what you find is that initially performance goes up, right? So your model gets better and better as you're doing reinforcement learning on the x-axis. But if you continue to optimize for your proxy reward function, eventually you overfit sort of your reward model, and your model starts to get worse, right? So that's the bending down of the curve on the top left, or sorry, on the leftmost panel. Actually, when we run this thing on the simulator, we can replicate this over-optimization behavior almost exactly. That's the middle panel over here. And as kind of a baseline, if you just prompt GPT-4 without carefully designing the prompts, you actually get something on the right, which is a very different behavior in which you would falsely believe that the best reinforcement learning algorithm is the one that most aggressively optimizes the reward model. It was kind of nice to hear at the ICML keynote this year that John Schulman basically gave us a shout out for being able to replicate this over-optimization behavior. The last validation that I kind of want to talk about, yes?
Oh, thank you. The human mode agreement, this is a correlation, right?
Yes.
And what is significant, like, if, for example, the difference between 0.6 and 0.63, is it significant or is it just like noise level?
Yeah. The y-axis here is somewhat hard to interpret, and that's why I always try to contextualize this as, the GPT-4 annotator has roughly the same agreement as inner annotator agreement. And I think the way to think about this is it's an internal validation. The left side panel is the more like true end-to-end validation. It complements that slide, not stands as its own interpretable evaluation. Hopefully that's a reasonable answer.
Thanks.
Great. Okay. And so in some sense, the other proof of this whole system working is, can we actually train good models when we run our RLHF algorithm, right? Because I said re-implemented the baselines, so does our RLHF algorithms actually work? And the answer is yes. The two lines I want you to focus on is the SFT52K. That's the alpaca model, that's our baseline, no reinforcement learning done. And PPO is our re-implementation of the PPO algorithm. And we see a pretty substantial boost when we train and evaluate with the simulator. And as I said before, the human world basically matches the simulated world. And when we take alpaca and we RLHF it using human feedback, we get substantial improvements in pairwise win rate relative to Instruct GPT. And finally, we do see very different qualitative behaviors. The PPO trained RLHF model gives much more detailed, longer responses. We were kind of surprised by this, but we also don't see, really deep changes in things like factuality and so on. A lot of it is actually changes that we see on the surface behavior. I'm going to sort of skip some of this, but one of the follow-ups that we've done is we've extended this work to basically be able to evaluate and do similar things for tool use agents, which is a thing that people are really interested in now. Beyond this work, what I think is the bigger picture here is that being able to use language models to essentially simulate complex both deployment environments and annotators really allows us to do more replicable and also much easier research and development on these models. I'm not saying necessarily that these automated data or evals is in some sense a replacement for humans, but they allow us to test out ideas much more quickly and much more easily in a way that I think will empower academic research. So I'm very optimistic that this will be a useful part of the way in which we do some of our empirical work. Okay, so the second thing I want to talk about is probing who language models emulate. In the previous section, I basically told you, okay, language models can be used to simulate, in some sense, human preferences, right? That's what we were talking about with the RLHF part. So if that's true, right, they're emulating some people, who exactly are they emulating, right? That seems like a pretty important question. And this is actually a really hard question, because language models are complex combinations of many different steps, right? During pre-training, they might be emulating internet users. And on the left, is basically the demographics of people on various internet forums. You might be emulating people from Reddit or Facebook or who knows what, right? On the right side is the demographic distribution of annotators in the InstructGPT paper. And that's actually very, very different. It's, college-educated Southeast Asians and Americans, actually. And so, like, who exactly are these models imitating? And on subjective tasks, like rating tasks, understanding this is just really important, right? And so now we want to understand, the default behavior of these models. In particular, we want to understand like whose opinions and subjective preferences are these models reflecting in their outputs. And our approach is going to be to compare language model outputs to public opinion surveys, right? So we know that language models are really good at answering multiple choice questions. We use them all the time in things like, evaluating factuality in MMLU or in reasoning in ARC, right? And so we can use the same kinds of ideas, but apply them to public opinion polls. And the nice thing about public opinion polls is that, let's say the Pew surveys have gone out and collected how Americans would respond to the exact same questions. And so then that allows us to basically compare language model responses to human responses on these same public opinion polls and allow us to start to answer the question, whose opinions are language models reflecting? And so a basic question you might start with is, okay, so if we look at these opinion distributions, is that close to the average American? And the answer is no. It's very much no. And LLMs have really high disagreements with the average American, where average American is defined by the Pew as some weighted average of the people they polled. And just to contextualize some of these disagreements, so what I'm measuring here is the Wasserstein distance between the language model's probability outputs and the Pew opinion poll results. And Da Vinci, the base LM, is at 0.8 disagreement. Just to contextualize that, that's about as much disagreement as Democrats and Republicans on climate change. So that's kind of not good. If you instruction tune this, it turns out it gets worse. It's a little bit worse than agnostics and orthodox on abortion. You can kind of imagine these are fairly strong disagreements between different groups. And now, you might ask, okay, so the Pew has these really nice detailed breakdowns by topic, so that those are the different rows. So these are different topics that people have polled for, in different demographic groups. So on the left panel is, political leaning, middle panel is education, and the right panel is income. So we can test, how LM's responses to polls align with these different groups. And I'm not going to drag you through all of the different elements here, but there is one high-level takeaway that I think is very interesting. So if we look at just the base models that we tested, they actually have a pretty similar distribution. They're generally, not really terribly aligned on political ideology with any group, maybe moderates to conservatives, low education level, low income, right? That's the opinions that they most closely align with. Now, we then take the models that have increasing amounts of human feedback, so Text Da Vinci 1, 2, and 3. And we see a pretty clear pattern. As we increase the amount of human feedback, we see more alignment with sort of liberal groups and more alignment with education, highly educated groups, and more alignment with high-income groups, right? So the feedback training really shows clear signs of, aligning the model towards, let's say, like better educated defaults, right? I'm not going to really weigh into whether, things like the political leanings are, intentional or not, but we definitely see some clear trends happening here. And one thing that I think is also really interesting is thinking a little bit about some of the details here. So if we look at what's exactly happening here, we start to see maybe some overfitting to the annotator distribution. What I mean by that is, let's say we look at the same kind of plot. So the columns, once again, are models. The rows now are different religious groups and age groups. We see that for the base models, generally aligned with Protestants and Roman Catholics. But then the feedback models somewhat mysteriously have a different trend, in which they're maybe more aligned with Buddhists, Hindus, and atheists. And all the models are not really very well aligned with people that are old, especially 65 plus folks. There's very little alignment with those opinions over there. If we look at the InstructGPT annotator pool, this actually lines up pretty closely in the sense that the people providing RLHF feedback are college-educated Southeast Asians, so that makes sense with sort of the religious affiliation. And also, there's not a single annotator that's 65 plus, so that makes sense with sort of the alignment to the age group alignment. This is not really conclusive in any reasonable sense, right? What does multiple choice tell us about any of this? But it is a very interesting lens to potentially the kinds of opinions that the system is reflecting. Okay, so now you might ask, okay, we can prompt language models. Can we prompt them to act like demographic groups, right? This is a pretty important thing because I think people are using this for things like product testing in a pretty crazy way. So we prompt LMs either by putting in a response to a survey or asking people to role play, or LMs to role play, and then we give sort of the question prompt. And what happens is that this does improve the alignment with the groups we're prompting for, but not as much as you would expect. So the x-axis is sort of the default alignment that we have on the rows, on the x-axis here, and the y-axis is what happens after prompting. So if prompting fixes all our problems, you'd expect to be at the very top of the y-axis here. And so we only see slight deviations from the x equals y line, which suggests that sort of steering and prompting generally improves things, but not by that much. Finally, you might ask, okay, what can we possibly learn from these multiple choice polls? Shibani, who was the first author, started to probe essentially do these biases or do these leanings translate over to free response? We had some initial results, but I think this is still really very much an open problem to do this rigorously. And in sort of follow-up work with Lisa, we started to start more formally study some of these questions in a thing that we've called generator discriminator or generator validator consistency, in which we're basically trying to see how often language models are consistent when we ask things like multiple choice questions versus when we ask the same questions in free text form. And our result, at least from that, is that this kind of consistency is a bit of a mixed bag. It's not that consistent, but it can be improved via fine-tuning, and the best models we have today are actually more consistent. Okay, so to recap at least this opinion part, right? Language models don't really reflect the opinion of the average American or any other group, and we should sort of disabuse ourselves of that notion that these are somehow simulacra of subjective opinions of individual groups. Human feedback does cause pretty clear shifts in how LMs respond to the survey questions we posed, and they can be steered, but they remain far from matching humans even with prompting. So the open question that we have here is the LM's multiple choice responses consistent in other contexts? I think this is in some sense a really important question. There's been dozens of papers written now, including ours, on using these kinds of multiple choice human surveys to probe language models. It is not really clear to me how far those results can be taken and how externally valid they are. And so there's sort of an important question of whether we can really sort of scientifically validate some of these things. Okay, so now I want to get into the third part. So in the first two parts, in some sense, I was dealing with subjectivity, right? I was dealing with questions of thumbs up, thumbs down ratings, and then I asked, okay, who are these language models imitating? And then you might ask, okay, it doesn't make sense to ask language models these subjective questions, right? We should be only thinking about language models in these objective capabilities questions like facts, right? But then you start to run into this problem. Language models are cool, but how do we know that the very best language models we have today haven't trained or haven't seen the test sets that you're evaluating on, right? And that seems like a pretty challenging problem. And so I'll talk about some very recent work that I think that's going up on arXiv today, proving test set contamination. So now let me sort of talk you through why I think this is a pretty big problem, right? What's in the training set of a large language model? Large language models work really well because they consume enormous amounts of data. So this tree map is from the pile, and it shows sort of the breadth of data that it consumes, right? It consumes a scrape of the internet through the pile CC. It consumes arXiv, it consumes GitHub, it consumes all sorts of things, right? And because of its scale, it's lightly curated, right? No one actually looks through this entire thing and decides, okay, this is what I'm going to include or exclude. And so what does that mean? Well, if we look into here, like maybe your test set for like, coding is somewhere in GitHub, right? Like we have no idea whether it is actually in there or not. And if you go on GitHub and you actually start to like search for things, you'll find that like basically every test set that you might care about is somewhere on GitHub, right? So that might be a little bit concerning if you start thinking carefully about this. And really, like, this concern has been, rising and rising and rising, I think, ever since the start of pre-training. But really, I think GPT-4, I think, has like kicked it in high gear because they basically stopped even publishing test set contamination studies. And there's been sort of a lot of, talk about whether something is contaminated or not. On the left one, this is something I thought was very clever. There was a post about how, okay, GPT-4's performance on code forces, on things that are, before 2021, it gets 100%. After 2021, it gets 0%. Isn't that a little bit suspicious, right? On the right side, there was a recent paper. It's a follow-up to the textbooks are all you need paper that I mentioned, right? It did really well on grade school math. And then there's a question of like, actually, if you like truncate the problem halfway, the model is able to like complete the problem and then answer it. And then, the Twitter post like, isn't that suspicious, right? But I think, these are really interesting and really important things to be doing. But also, these are sort of, heuristic accusations, right? Like at the very best, like, okay, yes, but maybe you really did get those code forces problems wrong for reasons other than test set contamination. We can never really know unless we have some way of looking into the model or proving, in some sense, contamination, right? And so what we really need, what I want to move towards, is going beyond this kind of, one-off case study on social media, God forbid, but actually giving, really precise proofs of test set contamination. And so what I'll talk about today is to show that this is viable, that it is possible to give this sort of very precise statistical test for test set contamination, and to give you some of the first results that we have along these lines. I think this is sort of a first step. I think much better things can be done, but I think even showing that it's possible is going to be worthwhile. Okay, so our setup is going to be that we are going to have a test set that we care about, and that test set will have a particular, hopefully mild assumption associated with it. And we are going to also be able to query log probabilities from a language model. I think that can be relaxed, but that's my assumption for now. Now, what I'm going to return to you is a statistical test that can flag test set contamination, so whether or not this test set was used during pre-training, with a type 1 error rate of at most alpha, right? So that means I'm going to give you a precise false positive rate guarantee, regardless of the model, regardless of whatever else you do to the world, right? So you can think about this as your frequentist hypothesis test. Go back to Stat 101, right? The null hypothesis is that the test set and the model are independent random variables, and the randomness that I'm considering here is the draw of the data set and the training randomness of the model. Okay, so the one-liner for how this is possible is exchangeability, right? Our starting observation here is that most test sets are exchangeable. What do I mean by that? You can basically shuffle the ordering of all the examples in a test set, and it's not going to change the underlying distribution, right? This is a core assumption in almost all of machine learning. We say all the time, assume that the data sets are independent and identically distributed. Exchangeability is a strictly weaker notion, right? So now, let's say our test set is exchangeable, right? It's exchangeable, but during pre-training, our language model has seen this test set. If that's the case, then it might memorize the order in which these examples appear. And the only way for a language model to know the ordering of these examples for an exchangeable test set is to have seen it during pre-training, right? So this provides a very straightforward test of contamination. Basically, any preference for a particular ordering that, let's say, is on GitHub is going to be some proof of test set contamination, right? So that's the high-level idea. And the full test that we have here is, in some sense, pretty straightforward. What we're going to do, I'll walk you through the ideas here, right? So the first thing that we can do is, okay, so now we know that our test sets are exchangeable, and so the language model should be invariant or agnostic to the ordering of the test set, right? So what I can do is I can compare the log probability of the test set in its original ordering versus all the possible random shuffled orders, and if this log probability of the original ordering is much higher, then we flag this model as having contamination, right? So that's the naive permutation test, and this gives exact control of the p-value and the false positive rate. But actually, there's a somewhat more nice thing that you can do, which is to cut the data set up into tiny pieces and then basically do shuffles over each shard and then compare the log probabilities within each shard and aggregate all of those pieces using a t-test. So the actual procedure is here. We're cutting up the data set into pieces. We compare the likelihoods of all the orderings, and then we compare to the mean, and then we do one big t-test, right? So this one's not finite sample valid, but it gives the same kind of guarantee, much more computationally efficient and much more powerful. But the upshot here is that all of these procedures give you what I promised you, which is that now we can provide very precise false positive guarantees on detecting contamination. So does this thing actually work, right? So to show you that it works, I need a case in which I know that there is test set contamination. So we trained a 1.4 billion parameter language model with 20 billion tokens, and then we injected a bunch of data sets into this model so that we know which data sets are contaminants, right? And so all of these data sets on the rows here are known contaminants for this 1.4 billion parameter model. And if these data sets appear more than 10 times, we basically nail it every single time with p-values that are essentially numerically indistinguishable from 0. So this means that this test is extremely powerful once your test set appears more than a few times, right? So we have a 100% detection rate. Unfortunately, we don't get to detect test sets that only appear once. I think this is still sort of a major sort of open problem that we have to solve, but this is very encouraging. And if we look a little bit more closely, you might ask, okay, what's the point at which we stop being able to detect these data sets? We actually get detections at both duplication counts of 2 and 4, right? So if a test set appears more than once, we have some shot at identifying it using our statistical test. And so this basically says, we can detect around 2 to 4 duplicates for test set contamination. And then finally, I think the thing that I think is most exciting is then to use this method to try to audit or to detect test set contamination in actual models that exist today on data sets that we care about, right? And so this is the last result, and I'm going to talk through this slowly because it also has a bunch of caveats that I want to talk about. So we tested all of these benchmarks. So ARC, this is a reasoning data set, Boole Q, GSM, Lambda, Natural QA, OpenBook QA, and PIQA. All of these are hopefully benchmarks that you've seen used to evaluate language models, and people have been concerned that because they've been around for a while, they've been contaminated in the training of these models. And we evaluate several open models from GPT-2 to Llama 2.7b, and we have a model called BioMed-LM. This is a model that's only been trained on PubMed data, and because of the nature of PubMed, it is almost certainly not containing any of these benchmarks, right? So you should think about this last column as a negative control. If we flag any data sets here, that's basically a problem. And we find that, of course, we don't flag any data sets here because, we have this nice false positive guarantee. And then for the most part, the open models that we have today don't actually trigger our contamination test on any of these data sets. So what's the conclusion here? My interpretation of these results is that we don't see evidence of pervasive test set contamination on a lot of the models we're using today, right? From the results just 2 slides ago, we basically get extremely powerful tests for any data set that appears more than a couple times, suggesting that these models, if they've consumed these test sets at all, probably only once. Right? The only one exception here is Mistral 7b for ARC, which does have a pretty low p-value. But for what it's worth, I will highlight and say that because of multiple testing reasons, this isn't as small as you maybe think. Finally, we did also test MMLU. This has been the big benchmark that people evaluate language models on. I add a little dagger here because MMLU is actually a collection of many small data sets. And some of those data sets are very much not exchangeable. And so we had to exclude them. And these p-values shouldn't be interpreted the same way as the rest of this table. But what we do find is small p-values on both Llama and Mistral. And what's actually interesting about this is that the Llama 2 paper actually says that they identified test set contamination on certain subsets of MMLU. So this is also consistent with what's known about these models. Okay, so finally, I think this is actually kind of an exciting sort of direction for language modeling research in the sense that we understand relatively little about language models, but we can actually build these kinds of provable guarantees on top of language models. What I told you about today was work in doing provable detection of test set contamination. But we can also do things like, build watermarks that have provable guarantees for provenance, right? So this is also a similar kind of false positive guarantee applied to detecting model-generated text. And this is something that Rohith worked on with me. And so this, I think, is a really interesting angle for combining theoretical work also with empirical language modeling. Okay, so I think I'm at time, so I'll wrap up now. We had 3 parts to this talk covering different aspects of improving transparency and understanding of language models. In the first part, I tried to show you how it's possible to replicate complex data pipelines like reinforcement learning from human feedback. And I showed you which components of that are actually hopefully helpful. In the second part, we built ways of analyzing the opinions that language models reflect using probing with public opinion polls. In the last part, I showed you some emerging work from our group on detecting test set contamination using permutation tests. Thanks, and I'm happy to take any questions.
Very nice talk. Thank you. A lot of interesting stuff. One thing, I would like to make a comment that shift that you observed when with RLHF or with human training. Well, if you actually look at the original paper of OpenAI, they very explicitly said that what they want. They align the values of those trainers who were mostly from South Asia, I think, to like explicitly to OpenAI internal values. So, and presumably OpenAI, employees are probably not quite reflective of the general population in the US. So just a comment.
Yeah.
Why would you expect to see exactly this?
I think I agree with that. And there's, I think, really interesting subtleties in this as well, whether these are just correlates. Like you might imagine that all they want to do actually is make, LMs more aligned with like educated people. But that, because of demographic correlations gives you sort of the other stuff, right? Because LLMs are a big box of correlations. You get some of these sort of unintended secondary effects. I also think there's been a lot of interesting work, say, by Anthropic on trying to do like democratic inputs to LMs to let people shape how the LM's values are decided. And I think that's actually just like a really interesting socio-technical problem.
Thanks.
Hi, Julia Hockenmeyer. Hi. So just about the last part of your talk. How exchangeable is natural language actually? I mean, like, how do you, how large are your shards? Because we have all sorts of sort of discourse effects and so on, right? So within documents and so on. Just like linguistically, it's a little bit unclear to me how, whether that assumption is actually valid.
Yeah,
and the other question was, how do your results depend on like both the amount of training data that these models have been exposed to? So basically, what fraction of the data was, is in this data set, and basically the number of parameters of this model.
Yeah, those are really great questions. So for the first question, which is about the exchangeability of things like discourse structure, we only look at basically data sets that have this like kind of single record format. So it's true that, for example, let's say we're going to talk about ARC because that's the one that flags. ARC is formatted in like a JSON-L, so it's a single record with different elements inside of it, and so each record should be shuffleable. If we're looking at something like news articles, of course you can't shuffle each line, right? Like that's completely nonsensical. And just to make sure we are keeping ourselves honest, that's why I run this Biomed LM. So of course we're checking to try to make sure these things are exchangeable, but we can never be sure with data sets that we didn't construct. And so we're using a known model that doesn't have the contaminants. And if they are non-exchangeable, this thing will flag. And we've seen that in some of the false positives that we picked up, in which this Biomed LM model will basically say contaminated when that's not possible.
Right. And what about GPT-3 or 3.5 or something like,
Yeah, so
GPT-2 is pretty old by now.
Yes, right. And the reason why we haven't done that is because this particular work was based on using log probs, and they pulled the log probs from the models. We have ideas for how to run this exact same test without any log probs, and when we do that, hopefully we'll have new columns in here or a new report about that. But we're thinking about it and working on it. And then what was the last question? Oh, scale. Yeah, we do have like sort of scaling results that we've actually been putting in and thinking about. All of these are with 1.4 billion parameter models, which are much smaller than a lot of the models people use. And the memorization literature is pretty clear that scale just improves this. So I expect the power to actually be stronger on larger models. Yeah, so we don't see a phase transition at scale, but we do see some phase transition-like effects with data set size. If it gets too small, it's impossible to detect no matter what we do.
So let's thank the speaker.